Hello students, welcome you all. So in spectroscopy, today I will discuss the introduction of UV-visible spectroscopy. So in spectroscopy, we usually interpret the spectra to determine the structure of any unknown compound. So if we have any spectra and we have spectral values, so by interpreting the spectral values, we can get some information about the molecular structure of some unknown compound. And one of the method is the UV visible spectroscopy. So the spectroscopy, what this spectroscopy is, in spectroscopy, any compound that interact with any matter or compound interact with electromagnetic radiation. So the spectroscopy is the interaction of matter or interaction of molecule with electromagnetic radiation. So these radiations get absorbed by the molecule. If any electromagnetic radiation falls on any molecule, then the radiation that can be absorbed by the molecule, and it is absorbed in accordance with the relation delta E is equal to h nu. So these radiation get absorbed according to relation delta E, this is equal to h nu. So this is very important line. So the radiations get absorbed according to the relation delta is equal to h nu. So where this nu, or we can write this as hc upon lambda. So where nu is the frequency of radiation. So this is the frequency of radiation. So suppose if we have molecule, any molecule is present, and if any light, electromagnetic radiation, suppose either UV visible light or infrared light, and that or microwave light, it falls over the molecule. Suppose if it is a UV visible light, if UV visible light falls over the molecule which is present in a ground state, then, and this electromagnetic radiation is having the frequency nu, and energy corresponding to this frequency nu is suppose h nu, and h nu is the energy of this radiation. Frequency of this radiation is nu, and the energy of this radiation is h nu. So what this spectroscopy, general principle of electrospectroscopy tells, this frequency of radiation will get absorbed only when the energy of this light is equal to the difference in energy of the ground state and excited state. Difference in energy of ground state and excited. Then only this frequency or this energy or this electromagnetic radiation will get absorbed. So when the difference in energy between the ground state and excited state, that is delta E. So when difference in energy between ground state and excited state, delta E, become equal to the energy of radiation, then only the absorption of light will take place, and after absorption of light we get the spectra, and we interpret the spectra and we can determine the structure of unknown molecule. So this is the main principle of any spectroscopic technique. So what this principle tells, when a molecule absorb the radiation, only when the difference in energy of ground state and excited state delta E become equal to the energy of radiation. So energy, the light is absorbed only when delta E become equal to the h nu, then only the light will absorb, and after absorption a spectra appears and we can interpret the spectra. Okay, so so same thing is then these radiation get absorbed according to the relation delta E is equal to h nu. So this is the electromagnetic radiation is absorbed, and we have a different region of electromagnetic spectrum. So let us see region of electromagnetic spectrum. So suppose let us see the different regions of electromagnetic radiations. So suppose this is UV range, and then we have a visible range, and then we have infrared IR, and then we have a microwave, and then we have radio waves, and this then X-ray, gamma ray, and cosmic rays. So the energy of these cosmic rays are the highest, and here the energy of these radio waves are lowest. So energy is highest over here, highest energy, and wavelength is low, and if energy is high, then according to this relation the frequency is also high. Frequency of this radiation or energy of this radiation is very high. If we go from radio waves to this cosmic rays, here energy and increases, wavelength decreases, whereas here this radio waves, it has frequency is less, energy is less, and the wavelength is more. So what happens if these different types of electromagnetic radiation get absorbed by the molecule? So if this radio waves absorb, so this region of electromagnetic spectrum, if this radio wave electromagnetic radiation is absorbed, then it gives rise to the study of NMR and ESR spectroscopy. In NMR and ESR or EPR spectroscopy, radio waves are absorbed by the molecule, and if radio waves are absorbed by the molecule, then change in nuclear and electronic spin takes place. So here change in nuclear spin and electron spin occur. This takes place in NMR or ESR spectroscopy. Okay, now in microwave spectroscopy, a rotational change occur in a molecule. After absorbing, when the microwave radiations are absorbed by the molecule, then rotational change, the molecule undergo rotation, it starts rotating, and rotational transition will take place, we can say. Here we can say rotational transition occur after when it rotates, and rotational transition takes place, and rotational transitions takes place by the molecule which show change in dipole moment, by molecule which show change in dipole moment. So this gives a rotational. So if microwave radiations are absorbed, then that is the part of a rotational spectroscopy. In IR, if IR radiation are absorbed, then this is a part of this vibrational spectroscopy. So vibration starts. So if vibration starts, then vibrational transition takes place. Vibrational transition occur. Now, so this is the visible region. This is UV and this is visible. This is our visible spectroscopy, or this is UV spectroscopy, this is visible. So UV visible spectroscopy we can say. So here this region is for UV visible spectroscopy. So in UV visible spectroscopy, what change occur? So change in energy of outermost electron occur only. So if outermost electron, that will absorb the energy and they will undergo change in energy. That is, they will excite from ground state to the excited state. So in UV visible spectroscopy, change in energy of valence electron or outermost electron. Whereas in X-ray, this if X-ray falls over the molecule, then it is about the X-ray spectroscopy, and here change in energy of inner electron occur. So here change in energy of inner electron. In gamma ray, here it usually it is concerned with the Mossbar spectroscopy, and here the rearrangement in the nuclear particle occur. When gamma ray are absorbed, then rearrangement in nuclear particle takes place. Okay, so this is about the different region of electromagnetic spectrum, and when different electromagnetic spectrums occur, then different change in a molecule occur, and they give rise to the spectroscopy, or they give rise to the spectra after absorption of these radiations. Okay, so now if you will see here we are concerned with the UV visible spectroscopy, and the range, if you will see the range of UV visible spectroscopy, what is the range? So how we can explain the principle for this UV visible spectroscopy? In the same way we can explain in interaction of molecule with UV visible radiation takes place, and these radiation get absorbed according to this relation. After absorbing the radiation, the electron will get excited from ground electronic state to the higher electronic state, or we can say electron get excited from HOMO to the highest occupied molecular orbital to the lowest unoccupied molecular orbital. So highest occupied molecular orbital to the lowest unoccupied molecular orbital, electron get excited. So the range, if you will see the range, then approximate range for UV radiation in terms of nanometer, that is 200 to, it is approximately, in some book you will find 190 nanometer, so 200 nanometer to 400 nanometer. And we can again divide this one into two, that is near UV and vacuum UV. So this vacuum UV, and this is around 100. Here, though I have written 200, it is from 100 to 200 nanometer around, or 100 to 190 nanometer, and this is near UV, that is 200 to 400 nanometer. So this is vacuum UV. It is very high energy radiation, very high energy. It is very high energy radiation. Very high energy radiation, and it is so much high in energy that the oxygen molecule which is present in the atmosphere also absorb this radiation. So if we want to analyze any molecule, under this region, then first of all we should remove the oxygen from the UV visible spectrophotometer, and that requires the special equipment, that is vacuum arrangement should be there. So in this region, in vacuum UV region, the vacuum equipment should be there so that oxygen does not absorb this. So in this region, oxygen also absorbs this. Oxygen can also absorb this light. So we have to create a vacuum. So vacuum arrangement is needed in a spectrophotometer. So vacuum equipment is needed in spectrophotometer if we want to analyze any molecule in this region. So we need a vacuum equipment, a special equipment is needed so that vacuum is created and we can analyze the molecule in this region. Then next one, that is the visible region, visible radiation. And visible radiation, it falls under the around 400 nanometer to, it is approximate 400 nanometer to 800, and some book you will see the 700 nanometer. So this is the region. So if we see the spectra after absorption, we can get the spectra. And the shape of spectra, if you will see the shape of spectra, UV visible spectra, and this is drawn in between absorbance and wavelength, in nanometer. So what kind of spectra? The spectra that we obtained is a broad band is obtained. In UV visible spectra, we get a broad band. And why this broad band is why broad band appears in UV visible spectra, not sharp band? So what is the reason? So as I told when I gave you the electromagnetic spectrum, then first what was there? UV, then after UV, then it was visible region, then visible, then IR, and then microwave, like this. So UV radiation has these are very high energy radiation. UV radiations are very high energy radiations. So if we allow to fall a high energy UV radiation on the molecule, then there will be the electronic change. So UV light or UV visible light, what changes will occur? Electronic change will occur. Electron will get excited from lower energy state to the higher energy state, and these excitations are also accompanied with the rotational excitation and vibrational excitation, because this IR radiation and microwave radiation, they are very much less energy in comparison to the UV visible. So if we allow to fall high energy UV visible radiation, then it is also accompanied with some IR radiation as well as the microwave radiation. So that's why electronic change will occur, as well as the rotational and vibrational change will also occur in a molecule. So due to this reason that we get a broad spectrum. So why we get broad band? Why we get a broad band in UV visible spectra? So reason, for what is the reason? Because electronic transitions are also accompanied with vibrational transition and rotational transition. So vibrational transition will occur as well as the rotational transition will occur. Now suppose if we have this two electronic state. So suppose this is the ground electronic state E1 and this is the excited electronic state E2. Then this ground electronic state E1 is, and suppose this light falls over the molecule which is present in a ground electronic state, and here this UV light is so high in energy that this one of the transition possible is, this is one of the transition, but this electronic state is also accompanied with the vibrational states as well as the rotational state. So suppose this is the vibrational state and this is the excited vibrational state. Suppose this is V0 V1, in the same way V0 V1. So this is the ground vibrational state, and some rotational states are also present. So this is also accompanied with a rotational states. They are also accompanied with a rotational state like this. Okay, so suppose this is R1, R2 like this. This is the rotational state. So one of the transition possible is this. So this transition, so means this transition are also accompanied with the vibrational transition also can occur. So vibrational transitions are also possible. In the same way, this rotational transitions are also possible. So many transitions, you can see the many transitions are possible like this. So electronic transitions are also accompanied with the vibrational transition. So that's why we have many lines. Suppose this is electronic transition. This is electronic transition. They are also accompanied with many electronic transitions and many vibrational transitions. Many rotational transitions are there. And these transitions, they cannot be resolved by the UV visible spectrophotometer. So these transitions cannot be seen separately. Okay, and they cannot be resolved by UV spectrophotometer. So this is the reason that we get a broad band appears in UV visible spectra. Okay. Now next thing that we should explain in I will now explain little about the instrumentation. So let us see now the instrumentation part. Okay, so now first of all, suppose in instrumentation, with the help of this simple diagram, we can understand the instrumentation part of UVVisible spectrophotometer. Now first, suppose if we have any source of light. Okay, this is a source. Means either we need a UV light or visible light. So for UV, we need a this is a bulb, okay, or filament. We need a hydrogen bulb, hydrogen lamp, or deuterium lamp. Whereas for visible region, we need a tungsten filament. Okay. Now, so this radiation, this light falls over the prism. This is now prism, and then it goes to the monochromator. So this monochromator, it allows the passage of single wavelength of light. Now the single wavelength of light comes out, and this single wavelength of light, now this light is allowed to fall over the sample. This light is allowed to fall over the sample cell as well as the reference cell. Now this is the chopper one. This is the chopper, and it breaks this light into two parts. And it falls over the mirror over here. It falls over the mirror. These are the mirror 1, suppose, and this is mirror 2. This is mirror, and then it goes into the light is allowed to absorbed by the sample. Light is allowed to absorb by the sample. So this is our sample cell, and which is made up of quartz. This sample cell is made of quartz. So here we have a sample, and here we have a reference only. Suppose the sample is usually made in some solution, in some solvent. Okay, suppose if we want to take a spectra of some compound, then it is dissolved in some solvent, and that should be transparent one, having the very low concentration, that is filled into this sample cell. It is a rectangular cell made up of quartz, and here we put a blank, means the sample is not present, only solvent is present, which is called as the reference. Okay, now after some of the light is absorbed by this absorbing medium, and rest of the light, transmitted light, it falls over the detector. So this is our detector D1, this is D2. So this is our detector, and usually photodiodes are present in the detector, and then it goes into the amplifier, and after amplifier, the signals, these are the signals which goes into the amplifier, and finally it goes into the recorder, and we get a spectra over here, where the spectra is between the absorbance and lambda, and we get the spectra like this. A broad band is obtained. So this is about the simple instrumentation part of UV-visible spectroscopy. Okay, so now in my next lecture, I will explain the different types of electronic transitions which are possible when any molecule absorbs the UV visible light. Thank you.